Okay, we're very happy to have Sun Mengzhou from National University of Singapore to speak on the non-elementarity of cofinal extensions. Go ahead.
Thank you for the introduction. And this is an ongoing joint work with Huang Tianle, who is also known as Lawrence, I think. Okay, so in this talk, I will mainly focus on the cofinal extensions for models of fragments of arithmetic. And especially I will look at the elementarity of these extensions. And here's a general question. So what controls or decide the elementarity of a cofinal extension? And in the end, I will give I think it's a very good answer, which is the second order theory or second order structure of a definable cut. And what's happening in this definable cut will decide the possible elementarity in the cofinal extensions. And here's my plan. I will first have some introduction, and then I prove a theorem which says that if you have a countable model which fails to satisfy PA, then you always get non-elementary cofinal extension. And the last one is the one trying to answer this question. I will introduce a way to do the truth compressing. So I will going to compress the first order truth into the second order theory of a definable cut. Okay, and here's the basic background. We have the language of first order arithmetic to be this one, and we say that a formula is delta zero if all the quantifiers are bounded, and we can define sigma n and pi n formula respectively. Each has n blocks of alternating quantifiers, and we say the formula is delta n if it is equivalent to both a sigma n and a pi n formula, either over some model or over some theory. And we have two major class of axioms. The first one is the induction I sigma n. So it's an induction, but restricted to sigma n formulas. And the next one is B sigma n, which is the collection restricted to sigma n formulas. So collection means if for any x less than a, we can find a y, then there's an upper bound for this with this y. And x means the totality of exponential function. And PA is a union of all I sigma n, which is the induction for all formulas. And Paris and Kirby, they proved the fundamental result, saying that all these axioms actually form an implication chain, which means that each B sigma n implies I sigma n minus 1, and I sigma n implies B sigma n, and none of the converse holds, which means that because the union is just PA, so if a model fails to satisfy PA, then it is either at this level, so you have the collection, but you do not have the induction, and for this model we call it B models, or you have induction, but you do not have the next level of collection, and for this kind we call it I models. These two kinds of model, we will see that actually they have different model theoretic properties in some sense, and in this talk we will focus more on B models, but we'll also talk about I models. So here's the central definition: cofinal extension. Roughly speaking, it's the kind of extension which does not increase the height of the model. So which says that for any x in K, in extension K, we can find a y in the ground model such that x is less than y. So you can only add some new elements below some old element. And we say that K is an n-elementary extension if all the sigma formulas are absolute. And here we adopt the following convention. We just assume that all the models satisfy I delta 0 plus x. And since this theory proves MRDP, which means that under this theory, all the sigma 1 formula is equivalent to an existential quantifier, so that between any extension, we always get 0 elementary. So we just assume that we always get we always get 0 elementary for any extension. Okay, and if we want to look at the possible elementarity for cofinal extensions, here's one of the fundamental results proven by Gaffman, Dimitrokopoulos. It says that in the case of cofinal extension, it's like if you have certain kind of a certain amount of collection in the ground model. So if M satisfies B sigma plus 1, then you are guaranteed to have n plus 2 elementarity for cofinal extension. And in particular, if M satisfies PA, then all of its cofinal extensions are fully elementary. But today we'll look at models does not satisfy PA. And actually, this is kind of the opposite to the case of N extension. So recall that in the case of N extension, it's like if M has an N extension to some K, and it is N elementary, I should say this is a proper one. Then this will imply that M satisfy B sigma N. I think this is proven by Paris and Kirby. So in the case of N extension, it's like you have a proper elementary N extension, then in the ground model, you have certain amount of collection. But in the cofinal extension is that the amount of collection guarantees the amount of elementarity. So this is the minimum level of elementarity we get. And there are two directions. One of them is how much elementarity can we get? So this is done by, this is proven by K. So actually there are two parts. The first part says that if you are countable B model, then you always get a proper fully elementary cofinal extension. And the second one is a bit informal. It says that every sufficiently saturated countable model, it always admits a proper elementary cofinal extension. So no matter what theory you satisfy, no matter your I model or the B model, as long as you are sufficiently saturated, you always get a cofinal extension. So having a proper elementary cofinal extension does not give us extra information of the theory it satisfies. I think later Schmel proved that there is a notion he introduced called largeness or smallness. He shows that a model, I think it should be countable model. A countable model admits a proper elementary cofinal extension as long as it is large, and that is also a saturation notion. So that's a case of how much elementarity can we get. And today we'll look at the other direction, which is how much non-elementarity can we get. So we always get n plus 2, then can we have non-n plus 3? Or can we have like fail the elementarity at each specific level? So these are the questions we are going to answer. Oh, if you have question, you just say it. I can't see the chat box. And here's my first theorem, which says that if you start with a countable model and it fails to satisfy PA, then you always get a non-elementary cofinal extension. And in the future, I will show that actually the countable condition cannot be dropped. So there are two remarks. The first one says that if you are the I model, then this is a classical result by Paris. Then you can always do a cofinal extension to some K, such that the K satisfy the collection where where actually M fails. So M and K, they satisfy different theory. So this is non-elementary cofinal extension. And here we only need to prove the case of B models. And the second one is that actually we can, in our construction of non-elementary cofinal extension, we can actually require that it is get in this way. It is get by you can get the extension. So here is M. We can always get our extension K by first having a fully elementary extension L, but this one may not be cofinal. And K is the cutoff L. Here's K. And here we get fully elementary. And here, and K is the cutoff L at the same height of M. So that K is a cofinal extension. And we say that all the non-elementary cofinal extension we constructed can be get in this way. And this actually gives a negative answer in one of case paper concerning the cofinal extensions of fragments of arithmetic. And also this, as a corollary, we get a good characterization of models of countable models of PA. So a model satisfies PA if and only if it all of its cofinal extensions are fully elementary. Okay, so let's see how to prove this. Recall that we always assume that M is a B model, so we have two ingredients. One is the negation of induction, and the other is B sigma plus 1. So let's first look at what does the negation provide us. So first we all know that if you fail to satisfy sigma plus 1 induction, then you have a sigma plus 1 definable cut, which we call it I. And if we take this, the least witness of the sigma n plus 1 formula, then what we get is a non-decreasing total function g from I to m, which is defined by the conjunction of a sigma n and pi n formula. And moreover, the range of g is actually cofinal in M. So this is the negation of I sigma n plus 1 provides us. And moreover, if M satisfies B sigma plus 1, so by Gatman Dimitrokopoulos.
Mengzhou,
Yeah.
sorry. So a quick question. I remember I have asked this question to you before. So you said when you take the smallest cut. So a few words about whether it exists.
I take the smallest cut.
Right. So how do we know that there is a smallest one?
No, I do not take the smallest one. I mean, if the sigma plus 1 formula is like there is a W by W X, then the function G actually is goes from X to the least W.
Mm-hmm.
It might be the case that there's no minimal sigma plus 1 definable cut.
Oh, I see. So when you say that there is this sigma n plus 1 definable cut, so you take n. So which one do you take then?
It's just arbitrary cut.
It's arbitrary. So at this point, it's
yeah.
arbitrary. Okay.
Yeah.
And then this function is special.
I should say the minimum W. The minimum.
All right. Thank you.
The minimum. And if M satisfy B sigma plus 1, so by Gatman Dimitrokopoulos result, we know that we have n plus 2 elementarity. And this amount of elementarity, and under this amount of elementarity, we know that in a cofinal extension K, the same definition of G, we also know that G is a function from my initial segment to the whole domain, and also G is cofinal in K. This fact can be transferred to K. And this means that for any cofinal extension K, the domain of G will also define a cut J, and this J is cofinal is a cofinal extension of the original cut I. And in particular, if the cut I is just omega, then since we cannot have any proper cofinal extension of omega, this is the intrinsic property of omega, so that the J will be also omega, which means that in any cofinal extension of M, omega is still sigma plus 1 definable by the same definition. And that will be a bit important in the future. I will use it implicitly. And also, still, if omega is sigma plus 1 definable, then here's observation. We use standard system of I of M to mean that all the coded subset of I in M, and standard system of M just means the coded subset of omega in M. So here's the observation. We can use the first order formula to describe what is happening in our second order structure here, because we can make omega to be definable, which means that whenever we want to say whenever we encounter a first order quantifier over omega, we can just replace it by the quantifier over M, but restrict it to omega. And whenever we have a second order object, we can just replace it by the code. So let's say, for example, that we can describe this fact: zero jump is in the standard system. We can see that there's a code A such that this code A will code the halting problem, which means that for any I in omega, I is in A if and only if there's a computation S such that S should also be in omega, such that the I3 machine with input I halts with computation S, and this part can be expressed by the delta zero formula, which means that no matter you do the computation inside M or inside omega, they give the same result. So this A will correctly record zero jump. So that if we want to get a non-elementary extension, one of the easiest way in this case, in the omega being definable case, is just that we control the standard system of the cofinal extension, so that these two standard systems they satisfies a different second order property. And since the second order property can be described by the first order formula, we get non-elementarity in this case. And for the case of omega not being sigma plus 1 definable, actually it is even easier, which we can artificially make it definable in a cofinal extension. So here's a lemma. We can have a cofinal extension of M to make omega being sigma plus 1 definable. So so here's what we do. We add a coded non-decreasing function into K from omega to I. So here we use the fact that M is countable. M is countable, then the cut I is countable, so that it contains a subset which has order type omega. And we take the backjection of this subset and omega, and that will be the function f. And we add the code of the function f to the cofinal extension K, so that inside K we can see that there is a f from omega to I, and also we can see that G is also a function from I to M. So if we take the composition, it becomes it becomes a definable function, sigma m plus 1 definable function from omega to m, and the range of it is cofinal in m. And so that the domain will be sigma plus 1 definable, which means that omega will be sigma plus 1 definable in the extension. and also, as a side product, this I will become non-semiregular. The non-semiregular just means that there is a coded function f starting from a smaller initial segment to this cut, and the range is cofinal. And also some cut, I should say some definition of the cut being non-semiregular. This thing can be expressed by the first order formula. We can see that there's a function f from a smaller cut to the cut I, such that the range is cofinal. So we can describe this. And if we start with an m such that the cut I is semiregular, then actually we already get non-elementarity. Because inside the cut, the definition of because inside M, the definition of the cut is semiregular, but inside K, this is not semiregular. So let's look at the general picture of how to prove this. So basically, we just split into many cases. For the case of omega being sigma n plus 1 definable, we just extend the standard system such that the standard system, the two standard systems, they satisfy different second order property. So here, beta 1 model means it is a sigma 1 elementary substructure of power set of omega. And if omega is not sigma plus 1 definable, if there's a semiregular cut, then we do the previous procedure for this cut. And after adding this f, we know that inside K, this cut is not semiregular, and originally it is semiregular, so we get no elementarity. If originally there's no semiregular cut, then we just pick any cut I and do the previous construction. But here we know that inside the extension K, omega being sigma plus 1 defined, and we know that omega is always semiregular. This is
Mengzhou, one question at the last case, do we know that it's actually a non-vacuous claim? So there are models like that?
I think yes, but I cannot give it now. It's a bit complex. I think only for sigma 1 case. So there are sigma 1, there are models of P sigma 1 and negation of I sigma 1 such that there's no semiregular cut. And in that case, a semiregular sigma 1 definable cut means that it is a minimum sigma 1 definable cut. So it's like you have an infinite descending chain of sigma 1 definable cut.
Okay, thanks.
Okay, and in this case, so originally we can also write down the formula saying that there's no semiregular sigma n plus 1 definable cut, and inside the extension K, we can see that there is a semiregular sigma plus 1 definable cut, and in this case, we always we still get no elementarity. And what I want to mention here as a comment is that at least the amount of non-elementarity here. So here we can see that in the middle two case, we get non plus 3 elementary, which is actually the optimal, right? Because we always have n plus 2 elementarity by Gaffman-Dimitrov-Kopolov result. So these two are optimal. And here, if you write down the explicit formula for the first case and last case, you will get non plus 4 elementarity. So one natural question is that, can we reduce this one to non plus 3, this one to non plus 3? And the answer is no. And it's for this case. So for this case, there is some model that all of its cofinal extension, we get n plus 3 elementary. And currently, we do not know the case of the last one. And to prove this, we need to introduce the last part, which is the truth compressing.
So before you move on,
Yes.
can you say a little bit about how these extensions are built? So can you go back one slide?
Yes.
Right. So in any of these cases, how do you add these, or how do you build the extension to change the standard system the way you want it, or add the coded function?
Okay. So let me give a easiest example. So let's say omega is definable. So we are in this case, and suppose the standard system of them such that zero jump is not in here, right? And actually, the simplest way to do this is to just have zero jump inside standard system of K. And to build such a model, it's just very simple. It's just we consider the theory of them with the full parameter plus the A code zero jump. And this theory, we know that this is finitely satisfiable, so it must have a model. But this model is not may not be the cofinal extension, but that does not matter. We just take the cut of this model. So let's call it L. And actually, this is fully elementary. And we just take the cut of L to be K. And inside this K, we know that zero jump is inside the standard system of K. So that since M and K, they share the same point of view of omega, so the same. So if you write down this this property in the first order formula, then between M and K they mean the same thing. So you get no elementarity.
Okay, thanks.
Okay, but so maybe to follow up on that, so because you differentiate between properties of the standard system here by being beta 1 models and not, so I'm sure you have tried other choices, so something like just RCA 0 versus ACA 0. It didn't work.
It works, but
I see.
But this is not how do you say? This is not important here, and actually. If the standard system of M is beta 1 model, then you always get then you cannot get non-n plus 3 elementarity. I will prove in the future. I will prove that if the standard system of M is a beta 1 model, then all of its cofinal extension, you get n plus 3 elementary. So that's why they put beta 1 model rather than SA0 here.
I see. Okay, thank you.
Okay, so here is the theorem. So the first one is just what I mentioned. There is a countable M such that for any cofinal extension K, we get n plus 3 elementary. And actually, in the future, I will give a slightly stronger version. So actually, any countable M can be extended to such a model. And the second one is if we drop the countable condition, then we can actually get an M such that any cofinal extension we get fully elementary. So let's see how to prove this. So to prove this, we need to go into the third part, which is the truth compressing. We just mentioned that we can describe the second order property of this second order structure by first order formula if I is definable. Actually, omega is not important here. We can replace omega by any definable cut. And what is surprising is that actually the converse is also true. So if we fix a parameter, then we can describe what is happening in the first order for the first order truth of them inside this second order structure if this I is sigma n plus 1 defined. this is an informal statement. I will make the formal statement in below, and I will give this by a rewriting system. I will rewrite the arbitrary formula into some kind of normal form, and this normal form is closely connected to the truth of this second order structure. And also I will introduce a correspondence between the first order elementarity of the cofinal extension and the second order elementarity of its associated extension. So to introduce this, there are two ingredients for the compressing. One is the failure of induction, and this provides us the cofinal function g from initial segment to m, as we already seen here. And the second one is b sigma plus 1. So roughly speaking, it provides us the ability to do coding for delta m plus 1 from them. So we are going to use this b sigma plus 1 to keep pulling up the Scaling function of the formula on this structure, and then we turn first order quantifier into second order ones. So let's say, what does this provide us? So this is called encoding delta m plus 1 over the cut. So usually we say the formula is delta m plus 1 if it is equivalent to both the sigma plus 1 and the pi m plus 1 formula for all parameter in the model. But here, it is a slightly generalization. We say alpha is delta m plus 1 over some cut I, if alpha itself is sigma plus 1, and there's some beta, which is pi m plus 1, such that the equivalence only holds for the parameter I in a cut. And also we allow some other parameter where the equivalence holds for this x running over the whole model. So it's a slightly generalization of the original delta m plus 1 formula. And there's a folklore result saying that if you have b sigma plus 1 and x, then actually you can do coding for all the bounded delta m plus 1 definable formulas. And the following is a slightly generalization, which is called Chomura coding lemma. It says that if m satisfies b sigma plus 1 plus x, and here we need I to be sigma plus 1 definable cut, and alpha is delta m plus 1 over this cut I, then we can do the coding of this alpha, but up to parameter in the cut. So it says that for any upper bound b, there is a code c here, such that c code alpha up to x less than b, and I in the cut. So this C correctly record the information of alpha up to the parameter in the cut. And the next one is called the collection of alpha over I. It's proven by this is Bellinger, Chong, Li, Wang, Yang recently. It just it's some kind of collection, but relativize the cut. So it says that if any x less than a, we can find an I such that I is in the cut and alpha xi is true. Then we can have an upper bound for this I, and this upper bound is also in a cut. With another collection, but relativized to the cut. So to prove this is just we take the code of this alpha using the Chomura coding lemma, and we replace the alpha by this code here, and then we do overspill. Okay, so that's what we need to do coding here. So let's say how the compressing works. As I just said, I will state the compressing as a rewriting system. We are going to rewrite arbitrary formulas into some normal form. And here I will not give the whole proof. I will do the pi2 case and the sigma 3 case. And the general case is quite similar to the sigma 3 case. And here, for simplicity, we just assume that n is 0 and I is omega. And in the future, I will give the Janus version. So this is not important here. And so M is a model of B sigma 1 and negation of I sigma 1. And G is actually delta 0 definable from omega to M and it's cofinal. So I write it here. Okay, maybe not necessary. So for the base case, the pi2 case, for any pi2 formula, for any A, there's a B theta A B. It is equivalent to say that for any X in omega, if we consider the A less than GX, then by B sigma 1, there's an upper bound for the B, right? So, and this upper bound, we can take it in the form of some GY, because we know that G is a cofinal function. So no matter how large the bound is, we can just take a take a GY such that GY is larger than this upper bound, and this Y is in omega. So this is equivalent to the second one. This is quite trivial. We just use the fact that G is cofinal and B sigma 1. But the important thing is that if you look at the structure of this expression, the red part, what I highlight here, all the quantifiers that they are bounded if we regard G as a function symbol, right? And then we can do the following, and then we can show that the red part, the highlight part, we call it alpha. Alpha is actually delta 1 over parameter x and y in a cut. So it's like we can if we write down the explicit definition of G, then it should become either, I should say there is a UV such that Gx is equal to U and Gy is equal to V, and for any A less than U, there is a B less than V dot dot dot. Or we can say that for any UV, if Gx is equal to U and Gy is equal to V, then this implies that for any A less than U, there is a B less than V dot dot dot. And this equivalence only holds for X, for the case of X and Y in omega. So that is a delta 1 function over X and Y in omega. And you might think of this delta 1 over the parameter in omega as the very basic level of the hierarchy of arithmetic. It is almost recursive in some sense. And for the rest of this, for these two quantifiers, these are quantifiers over the cut omega. And then, because we know that this alpha is delta 1 over the cut, we can do the Chomura coding lemma to take the code of this. And actually the code is just the Scaling function of this for any X there exists Y. So if we take the code, then it is equivalent to say that there is a coded function F, which is a total function from omega to omega, such that for any X in omega, alpha X and Fx holds. And actually Fx is just the least Y here. So here we somehow turn arbitrary pi2 formula into this form. And but unfortunately, this one is not a real second order formula. This quantifier is not a real second order quantifier because it's just take the Scaling function of two first order quantifier over omega. But we will see that in the next case, in the sigma 3 case, we will get a real second order quantifier over the cut. Okay, so let's go to the next case. We let the exist F means that there exists a coded function F, which is a total function from omega to omega. And for sigma 3 case, it is equivalent to say that, So if we start with any sigma 3 formula, there's a C such that some pi2 thing is true. And by the last case, we know that replaces pi2 thing by the normal form. It is equivalent to say that there is a C such that there is a coded function f such that for any x in omega, alpha x fx c holds. And this one says that C is the correct parameter for any x in omega for this coded function f. And then we do the following trick. We turn a first order quantifier over the model. So there is a C in M is equivalent to say that there is a Z in omega and there is a C less than GZ. So this is a small trick just followed by G's cofinal. But here you can see that we turn a first order existential quantifier over the model to two parts. The first part is the existential quantifier over the cut, and the second part is a bounded quantifier. So that's the third one. And here you can see that we have a bounded quantifier here, and we have a universal quantifier inside, so that we can apply our collection over the cut omega. We apply the collection to push inside the bounded quantifier, and we pull out the universal universal quantifier over the cut. And that is the essential step for the sigma 3 case. So that is the final expression. And here you can see that the part that I highlight here has the same structure as the last page. You can see that all the quantifiers that are bounded, if we again regard this G as a function symbol, so that if we call it beta, then this beta is still delta 1 over parameter in the cut. Here is a bit technical here because for the parameter f, it is not an element in omega. But the point is, if you look at the definition here, we only use the information of x of this f up to x prime, which means that we can replace the f by the finite function from omega to omega, and that will be just one natural number, so that we can say that the delta 1 is over z and x prime and f restricted to x prime, and they are all in omega. And here for the rest, we got one existential quantifier, first order, and one second order quantifier, and the universal quantifier over omega. And this time, this f is a real second order quantifier. So let's look at the meaning of these two expressions, the third one and the last one. The third one is basically the same thing as the first one. It just says that up to some upper bound z, there is a C such that C is the correct parameter for any x in omega for this coded function f. But the last expression actually says something even weaker. It says that so this C is not the correct parameter for arbitrary x. It's like if you restrict this x up to the upper bound x prime, then for any upper bound x prime, you get a correct parameter C such that C is the correct parameter for x less than x prime. So that for different upper bound x prime, we may get different parameter C. But these two are still equivalent by our collection here. And the last one says actually it says something completely different. And in this case, actually the second order quantifier f is it becomes a real one. And if you examine the definition of this beta in detail, then you will know that actually if you fix this if you fix the z here, then this x prime and f restricted x prime satisfying this beta will provide us a omega branching tree. And actually, this f, it just says that there is an infinite path of this omega branching tree. So any sigma 3 formula just says that for some delta 1 definable omega branching tree, there is an infinite path. So is very similar or exactly the same as the sigma 1 normal form in the second order arithmetic. So that's the case of sigma 3, and the general proof is quite the same as this one. So here is a normal form. So under this, so under M satisfy B sigma 1 and negation of I sigma 1. Oh, I guess I need to hurry up. And omega being sigma 1 definable, then any sigma M plus 3 formula can be right into this normal form. We have M alternative second order quantifier and one first order quantifier all over omega. And this alpha is delta 1 over parameter in the cut. And this alpha is effectively decided by phi, and such equivalence is provable in this theory. So that the normal form actually says that for arbitrary formula phi in M, if we want to evaluate its truth, then actually we only need to know very little about M. We only need to know what is true for delta 1 formula over the cut. And then the rest of the computation, we can do it entirely inside the second order structure. So it's like so that's why we call it compressing truth. We compress the truth of M inside the second order structure. And also I want to mention that if we fix a parameter C here, then actually by Chon-Morat coding lemma, we can take the code of this alpha. And if we replace the codes by the corresponding second order object in the standard system of M, then this one will become a real second order formula inside this structure. So that's the meaning of I say that we can describe what is happening in first order for the first order theory of M inside the second order structure. Okay, so how does this normal form connected to the elementarity of general cofinal extension? To do this, we need to have have a little bit definition in second order arithmetic. So it says that a formula is R sigma 1M, a restricted sigma 1M, if it has this normal form. We have M alternative second order quantifier. Each means that there's a total function from omega to omega, and one first order quantifier. And this S we need to we require to be delta 0, 0. And actually the restricted version and the normal version, it is proven by CUNY. They coincide over AC0. But the problem is that because we are working in the fragment of arithmetic, so our standard system generally just satisfy WKL0, and we do not get AC0 in general. So we need this definition. And we write this to mean that these kind of formulas are absolute between second order extensions. Okay, so now we can state the correspondence. We need a lemma by Belanger and Huang. It says that if M satisfies B sigma 1, and we have a cofinal extension K, then K also satisfies B sigma 1. So that between M and K, they satisfy the same amount of collection and also the same failure of I sigma 1, so that they will share the same normal form theorem. The normal form given by M and K are exactly the same. And And here it says that we have first order elementarity in the cofinal extension if and only if we have the second order elementarity in the second order structure extension. And this correspondence can help us to convert the problem of the elementarity of the first order arithmetic into a problem of second order arithmetic. And what is a good news is that, so in our case, we want to construct models with special properties, and most of the time we can just make omega to be sigma 1 definable. So which means that the problem of second order arithmetic here, the first order part is omega, which means it is easier to deal with, and we have lots of machinery. We have machinery from second order arithmetic or even set theory. And here is one of them. It's called beta M model. So a second order structure is called a beta M model if it is a sigma 1M elementary substructure of the power set of omega. And Mumra and Simpson proved that this beta M model will form a hierarchy. So for each m greater than 0, we can have a beta M model, which is not a beta M plus 1 model. So that if we use our correspondence, we can get a cofinal extension where the elementarity can fail at each specific level. So here is the following. The first one is very simple. It just says that if we do not enlarge the standard system, then we always get full elementary. And the second one is that if we let the standard system of M to be beta M model, but not a beta M plus 1 model, then we cofinally extend it to some K such that in the extension K, it is either just the standard system of K is either just the power set of omega or elementary substructure of the power set of omega, so that in the second order extension, we get sigma 1M elementarity, but not sigma 1M plus 1 elementarity. Then by the correspondence, we get this amount of elementarity in the first order sense, but not the next level. So that means that we can fail the elementarity of a cofinal extension for B models at each specific level, as long as it does not violate the Gauss-Dimitri-Kopotzlos result. And the next one is what I mentioned before. So it says that if we start with arbitrary M0, then we can always cofinally extend it to some M such that the standard system of M is just the power set of omega, which means that you cannot enlarge the standard system anymore. So that for arbitrary extension of M, for arbitrary cofinal extension of M, you always get fully elementary. And if we want countable, then starting with any countable M0, we can cofinally extend it to some M such that the standard system of M is a beta 1 model, which means that we have sigma 1 elementarity between standard system of M and power set of omega, so that for any adequate standard system K, which is an extension of standard system of M, we also get sigma 1 elementarity here. So this is just a very simple model theory argument. And here the sigma 1 elementarity by the correspondence, it means 3 elementary here. So for any extension of M, we get 3 elementary. So it's like in the normal form, we see that any sigma 3 formula is equivalent to saying that there's an infinite path of some omega branching tree. And here what we do is just we put the infinite path already in this M, so that we always get 3 elementary, because in any cofinal extension, we already see the infinite path in the ground model. Okay, and here's the last one. It says that if we start with a countable M, then if we let the standard system of M to be the elementary substructure of the power set of omega, then we can actually for this M for arbitrary extension. So this extension may not be elementary or cofinal. So this is not important. We can have a further elementary extension L, such that if we consider the cut of L at the same height of M, we call it L bar. So L bar is an elementary extension. So L bar is a cofinal extension of M, and we get fully elementary between M and L bar. So this is done by we just look at the standard system of this K. Then no matter how extended, because we know that standard system of M is an elementary substructure of the power set of omega. Then we can further extend it to some even larger standard system L, such that we get fully elementary between the two standard systems. And this means that we get fully elementary in the first order series. And this answers another main question in case another paper. And in that paper, he tried to characterize models of PA in terms of the possible elementarity of cofinal extensions or some other extensions. And here the answer just says that for this condition, it failed to characterize PAA because there is some countable M such that it failed to satisfy PA, but it satisfies this property. And next, I want to say the generalized version. So we can replace B sigma 1 by arbitrary B sigma 1 plus 1. And also the cut omega, we can replace it by any sigma 1 plus 1 dividable cut. But here we need to close down the exponentiation due to some technical reason. And we have the same corresponding theorem. And what I want to mention here is that actually in the proof of the correspondence, actually cofinal extension does not play the important role here. So as long as we have K satisfy the same amount of collection, and we have enough amount of elementarity so that M and K, they share the same failure of the I sigma n plus 1, and they share the same point of view of delta n plus 1 formula over the cut, then we can still get the correspondence. But this time, in the second order extension, the J may not be cofinal in I, but we can still embed I into J. So that is the generalized version. I hope it will be useful in some sense, but I don't know any other application other than the cofinal extension yet. Okay, so here's the last slide. It's about the case of I models. So I think I need 1 more minute, and sorry about that. So all we need to so all we did before are about B models. So what can we say about the other level, which is the cofinal extension for I models? So first of all, as the Paris result, for arbitrary M, which is an I model, it admits a non-elementary cofinal extension. So this is even true when M is uncountable. So you can see that this makes a difference between I models and B models. In B models, we can have some models such that it cannot have a non-elementary cofinal extension. And for I model, it cannot. And the next one is by Adamovich and Kozak. Actually, it has nothing to do with cofinal extension. It says that under the theory, any formula is equivalent to the sigma n plus 1g formula, which is a closure of a sigma n plus 1 formula on the bounded quantifier and existential quantifier. So I list it here because I think this is some kind of truth compressing in some sense. We compress the formula of arbitrary complexity into this restricted version. So it's kind of like the same flavor of what we did just now. And last one is also interesting. This is essentially in Lassan's PhD thesis. It says that if M is pointwise sigma plus 1 definable, then actually there's a fixed M such that for any cofinal extension K, if we have this amount of elementarity, then actually we get fully elementary. So if we are above this level, then we cannot fail the elementarity. And actually, he says a bit more. Actually, what he says is that there's no proper cofinal extension with this amount of elementarity. And here we want to ask that, is the last property true for all M models, or is just some specific properties of pointwise definable M? And currently we do not have any idea about this. And I think that's all for my talk. And here's a summary. And thank you for listening. And sorry for the overtime.
Oh, definitely don't apologize. That's very great. So let's thank our speaker. And I will open up to questions.
Oh, there's a chat.
Yeah, someone just wrote thank you. Yanis Siligat.
Oh, you're welcome.
Oh, thank you. So, okay. I'll open up for questions.
This is, I don't know, a silly question. Is this written up anywhere yet? I can read through in detail.
No, I plan to publish it on archive. I think in maybe a couple of months. I don't know.
Okay, awesome. I'll keep my eyes out for it.
Okay, if I publish it, maybe I can send you a notice.
I mean, if it just is on the archive, I'll see it.
Yeah, yeah, it's on. I mean, publish on archive.
Just a small question about this last from Lassant thesis.
Okay.
Is there anything you can say about that M? I don't remember.
So
the previous slide, the Lassant's theorem.
So actually the procedure is like this. So if M is pointwise sigma plus 1 definable, then actually inside M, omega is definable in it. So there's a fixed definition of the omega. Okay, thank you. So that there's a fixed definition of omega inside M, and we can write down a sentence describing that M is pointwise sigma plus 1 definable using this definition of omega. And if K is a cofinal extension of M, then inside this K, the same definition of omega will apply to K. So inside K, the omega is still definable in K, so that if we have enough elementarity to make the formula saying that M is pointwise sigma plus 1 definable to be absolute, then K will also know this, so that inside K, K should be also pointwise sigma plus 1 definable. And in that case, if there's a new element in K, not in the ground model M, then this new element should be sigma plus 1 definable. And if we write down the formula defining it, and we know that inside K, it says that there is an M satisfy this definition, and inside M, there's no M satisfy this definition. And this makes a difference. And if we have the elementarity to guarantee that this thing cannot happen, then we get this here. So it's just it's just as long as you write down the exact formula, you know what is exact.
But in other words, it may not be the same for all sigma n plus 1 definable M's, because it may depend on the nature of this sigma 1 definability.
No, I think the M is universal to M. It's just some.
Oh, I see. You just need to count the number of quantifiers or something.
Yeah.
Oh, I see.
I think 7 or 8 should be enough.
I see. All right. Thank you.
Either.
I think someone raised hand.
Yes.
Is there any question?
Yeah. Thank you very much for a very interesting talk. I
Thank you.
have a question about the large. When we have when we have a cofinal extension, I think we can talk about the largest initial segment shared by both of these structures. What can we say about these costs? Do we have any results about the amount of elementarity of these costs or something else?
You mean the relation between this one and the largest initial the largest common initial segment?
Yeah.
So I think we have one, but not very hard. It's just a simple corollary. We say that if we have the M, here's our M, and here is the greatest common initial segment. Let's call it GCRS. No. And here is a definable cut. And if the cofinal, So here is K, M and K. So if the greatest common initial segment of M and K is larger than any of the definable cut I, then we get full elementary, because in that case, we know that M and K, they share the same point of view of, I should say, the standard system of M relativized to the cut I is equal to the standard system of K relativized to K, so that by the correspondence, maybe in the general version, we get fully elementary in this case. So I think that's maybe that's one of the connection.
Yeah. Okay, thank you.
Thank you.
Oh, I see. But this will not work when I is actually the greatest common initial segment.
No. In that case,
it may not.
Yeah. In that case, the standard system may not be preserved. So,
but still, we don't know what happens, do we?
Sorry, what do you mean by what's happened?
No, so the standard system is not preserved, but we can still get some sort of elementarity.
Yes, so that's depend on how much new paths you added in.
Right.
You adding into the standard system of K.
Right. What went wrong? The way, if anything, right?
Mm-hmm.
Okay. Any other questions? Okay. Let's thank our speaker again.
Thank you. Thank you very much.
Thank you for the invitation.
And next week, Saida will be speaking, Saida Bahrami, and we'll be starting earlier. Roman, do you remember the time that we're starting?
Yeah, well, just one hour earlier at noon our time.
Okay, we're starting 1 hour earlier.
Yeah. Sorry for the time.
Oh, no problem.
All right, no problem at all at this end. And Vika will send a reminder to everyone about that.
Okay. All right. See you all next week.